All right, this should be recording. We did some practice with one of the other people, but I forgot to record. So hopefully between people coming in and out, I can just go over some of these practice problems we went over. This is from a test, one of the previous tests. So we're just gonna go over that. The main thing we were practicing is just nomenclature. For this one, at first glance, you might just want to go across, but the thing, hold on, I'm trying to get my pen. Here. The main thing they have to pay attention to is the longest parent chain, the longest carbon chain, just period. So it's not, there's no ethyl group at all. They're all methyl groups because if we follow this line right here, all right, that's 1, 2, 3, 4, 5, 6, 7, 8. It's an octane. Then you have 3 methyl groups right here. Methyl, methyl, methyl. Let me make this thinner. I don't like it this thick. This word? No. Oh, here we go. All right. So this would be, or these are our 3 methyl groups, and you just number them back and forth, see which one has the lowest number combinations going left to right. I'm pretty sure that's the correct one. 1, 2, 3 methyl, 4 methyl, 5, 6. No, that's wait, yeah, 5, 6, 7, 8. So that would be 2, 3, 6, comma, no, wait, 2, comma, 3, comma, 6 dash trimethyl octane. Now for the next one, it's another situation where it might be first instinct to just go across. So like people might think 1, 2, 3, 4, 5, 6 carbons, but no. Again, longest carbon chain, you have to include this as well. So the carbon chain would be 1, 2, 3, 4, 5, 6, 7. It's a heptane. Now let's number the heptane with the lowest number denominations. So I'm just going to do this in my head. Save the hassle of trying to draw with the touchpad on my laptop. 1, 2, 3, 4. Oops. There we go. 1, 2, 3, 4, 5. 2, 4, 5. Then going the other way would be 1, 2, 3. There we go. 4, 5, 6. 3, 4, 6 versus 2, 4, 5. All the functional groups, the methyl or the alkane groups and the halogen groups, they're the same priority. There's no tie. The red format wins going left to right. It would be, let's see if I can type this again. Okay, cool. 2, 3, 4, 4, 5. Remember the dimethyl. Yeah. 1, 2, 3. Yeah. All right. Nope. Mouse. Let's clear. There we go. Down. Okay. Now this one you kind of haven't seen quite yet, but it's really easy. It's just adding another functional group to what you know. So you know how to include alkanes and halogens: chloro, iodo, bromo, fluoro. But right here, you notice, all right, we have an oxygen, but that oxygen is connected to another methyl group. So this is a functional group called an ether, and you will deal with these a lot throughout OChem. Obviously, it's a functional group, and especially in lab, because ethers are very great solvents because they're polar and they're very aprotic, which is very useful. But ethers are generally some kind of R group, oxygen in the middle, and then another R group. Obviously, the lone pair is the oxygen because it's polar and aprotic. And that's what we have right here. We have this first R group right here and the second R group right here. And they're both singly bonded, single bonded. Uh, it's 10 o'clock in the morning. I'm sorry. I should be more awake than this. To the oxygen. And that denomination is just called oxy. So if there's a methyl group attached to it, it would be methoxy. There's an ethyl group, it's an ethoxy. That goes on further. However, I doubt you'll see a group that extends beyond an ethyl group, but there's propoxy. All those common alkyl names that you are memorizing applies to this. Methoxy, ethoxy, it's really easy. And even though you know that the prefixes di, tri don't do anything for alphabetical numbering, the prefix for these oxys do matter. So ethoxy would be at the beginning of the name compared to methoxy because E is before M. They're mowing the lawn outside. Hopefully that doesn't become a problem. So methoxy is just normal functional group. There's no special denomination. So if we were to number these, hold on here 1 second. Okay. If we were to number these, it would be 1, because remember that O breaks that parent carbon chain. It's just a branch now. 1, 2, 3, 4. It's a butane. All right, now let's number these. So going right to left, this would be 1, 2, 3, 3 dichloro. Going the other way, it's 1, 2, 2 dichloro. And then 4 methoxy. Well, it's kind of a no-brainer. There's no tie here. You have to go right to left. So you have 1 through 3 compared to 2 to 4. So if we rename this, it would be 3, oops, chloro, oxy, oops, wrong one. I'm sorry, 1 methoxy. Now here is where we get into special groups. All right. We introduce alcohol groups and amine groups. And what's different about these branches is that they have to get priority no matter what. All right. So even if you have, let's say, a decane, 10 carbon chain, if every single branch group is like at the very end, like if, for example, you have, hold on, let me finish this compound. Then you have 1 alcohol group on the very first carbon, right? That first carbon has to have priority. So even if you have, you can have a compound like, trying to think of it, 8, 9, 10 di chloro, or 8, 9, 10 trichloro, 5 methyl decanol, right? Decan 1 all, because the suffix for alcohol is just OL, like methanol, ethanol. Let me draw it out. I don't want you guys visualizing this. This is more complex. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Let's just add some groups. So like if you had chlorine, Cl, that's a very ugly Cl. I'm so sorry. I'm doing this on a touch. And like, let's just throw in an ethyl group. All right. And we had all the way over here an OH. Right? That's an alcohol group. Now, it's first, hold on. I don't know what that's about. Sorry, I got a notification about Zoom. Our instinct is to go, oh, come on. Okay, that's why. Sorry, I'm having a lot of technical difficulties. Or not even difficulties. I'm the one having them because I am technologically inept, as it seems. You want to first off go that way. Initially, that's what you think because all the chloros are over there and you want low number combinations because that's where you're used to. Well, you got to throw that out of the window when you think about alcohol groups and amine groups because those priority groups, no matter what, even if all the other branch groups have high numbers, the functional group has to have the lowest number possible, even if it's one or two, not necessarily one, but just the lowest possible ever. This one, for example, right here, this is cyclopentane. It has two functional groups, alcohols and amines, and there's a hierarchy that you will get to know. Thankfully, yay! But alcohol groups are a higher priority than amine groups. All right, and when the alcohol group is present, the amine group just becomes a normal branch. It's just goes back down the hierarchy because what we want to focus is on the alcohol. And what you might be thinking, all right, well, if we have a cyclohexane, cyclopentane, cycloalkane, just in general, we want to think, oh, the first point of difference. If we do like 1, 2, 3, 4, that gives the lowest number combination possible. We want to go counterclockwise. That's incorrect because we have those functional groups and we have stuff that we need to prioritize. So the correct way to name this is, even though it's really weird, 1, 2, 3, 4. All right, let's add some text. It would be 4, whoops, amino spell cyclo. Oh, come on. Later. Okay, cool. I'm so sorry. More technical ineptness. Cyclo, pen, 1, 3, 5. You'll get into prefixes later, but just know that it goes against the norm, what you're used to, and just more practice about that helps a lot. Using that kind of logic that, all right, no matter what, alcohol has to have the lowest number scheme possible. Let's take a look at this one right here. Right here. Nope, that is not my job. Right here. So let's first off locate our parent chain. That would be this right here. Okay, it's the same thing as this. Same thing. Excuse me. But that's a pentane, and alcohol is on the third carbon. So no matter which direction you go, alcohol will always be the third carbon. So we don't really have to worry about direction. And now we just have to worry about our branch groups. All right. So if it's a 3-ol, we have our branch groups Cl and CH3. Now we have to think, all right, which direction do we go? Well, if our scheme would be 2, 3, 4, 2, 3, 4, back and forth, that's a tie. And the tiebreaker is alphabetical order. And alphabetically, chlorine takes priority over methyl group because C goes before M in the alphabet. So if we were to name this, it would be 2 chloro, 4, 10. Nope, not 1. 3-ol, like I said before. Yeah. And the last thing we should cover for nomenclature is the cyclohexane. Now, cyclic compounds are probably the biggest challenge for the first test because of how tricky they can be, and he will throw a bunch of tricks at you. Personally, when I took the first test out of my entire OChem journey, test 1, semester 1 was my worst test. I low-key bombed this this nomenclature stuff because I slept on it. I'm like, oh, that's so easy. Nah, I didn't study enough. I got a little cocky. I made up for it though. Test 2 and test 3 were dubs. Let's go to my draw. All right, well, cyclohexane, this is kind of a weird situation because you have, kind of a direction where you want to go, like first point difference. So wherever you start, you have to go toward the other branch. So if you always have to have schemes of 1, 2, 4, 5s, right? 1, 2, 4, 5, no matter where you go. All right, let's do it again. 1, 2, 4, 5. But the thing is, how do we denominate which number goes where? Well, if they're all tied right here, it's alphabetical. So what is the alphabetical priority? Well, let's look at the alphabet, right? B goes before chlorine and methyl groups. So B is what we want to start with, Br and Br. Now, which Br do we choose to start from? All right, do Br going towards the methyl and start counting that way, or Br towards the chloro going that way? Well, another tiebreaker, alphabet. But you got to go the chlorine way. So if we're to name it going towards the chlorine, let's do it in pink. I'm feeling pink. All right, 1, 2, that's just 3, 4, 5, that's just 6. Don't worry about that 6. All right, that's your number denomination. BR has the lowest number combination possible. If we start with BR, it'll be 1, 4 bromo both ways. All right, and chlorine, our next one, is also our second priority branch group because of alphabet stuff. Because tiebreaker again, that also has our lowest possible number scheme for the rules we're going with. So let's make this 2 texts. 1, 4 dibromo. 5 cyclo. Yeah. Let's not worry about this one just yet. I'm gonna wait. Yeah, not this one. We're gonna wait for Dr. Rigg to explain that. Well, some other things I would have you guys make sure you study. Isomerism, I doubt he'll go over isomerism again because you guys are going to be focusing on Hayworth structures and chair conformations, which is pretty confusing topic. So you can at least do this one. Oh, hold on, let me draw. You can do this one or those pairs, these pairs, because you're identifying what kind of isomers there are. And this one, these 3 you can do. Hell, let's do it. All right. I don't know why that bar is still there. Go away. There you go. Let's look at this one in the corner. All right. We have a 1, 2, 3, 4, 5, 6, 7. That's just a heptane. 1, 2, 3, 4, 5, 6, 7. That's a cyclohexane with a methyl group attached. 7 carbons. They're the same amount of carbons and they have the same amount of hydrogens because we have what? 3, 3, that's 6, 8, 10, 12, 14, 16. 16 hydrogens. Now we have 3, 1 right here, so that's 4, 6, 8, 10, 12, 14. Did I do that right? 6, 8, 10, 12, 14, 16. Oh, shit, I did that wrong. Hold on. Let me tally this up on a piece of paper so I'm not tripping and I'm not giving you guys the wrong answer. Hold up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16. Yeah, they're different. These are different. By the way, if you haven't read the instructions yet, I didn't really go over that. I'm sorry. For the following pairs of compounds, give the appropriate relationship between them. You have options that are the same, so they're exactly the same in terms of spatial arrangement and connectivity. Different, just different molecular structures. Like if you're going to compare methanol and ethanol, they're obviously different. Constitution isomers, different connectivity, and then stereoisomers, which we will get into. Do not focus on that. Yeah, let me double check. Yeah, they are different. Okay, cool. I'm not tripping. All right. This one we have 1, 2, 3, 4, 5, 6. We have 6 carbons. 1, 2, 3, 4, 5, 6 carbons again. All right. Maybe we're getting somewhere. This has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens. So C6, H12. Here we go. This one we have C6 again. We confirmed that has 6 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. H12. So they have the same molecular formula, but different connection because we have a cyclobutane with 2 methyl groups, and then we have a cyclohexane. So they are constitutional isomers. I would suggest that today you really study this stuff because your test is already this Friday. Just exposure, study yourself, seal yourself, just read over the definitions of what they are. Go over the practice test because that's literally what the test will look like. All right, let's take a look at this one again. This kind of messes with your brain a little bit, all right? So we have, this is our longest parent chain. This is our longest parent chain. And this is 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7 carbons are the parent chain, are heptanes. We have a 2, 3, 4, and we have a 1, 2, 3, 4 methyl groups. They are the same. My trackpad writing is atrocious. All right. And we've seen this before. You're given a very complicated structure. You have to identify, all right, what's a hybridization of each of these carbons, right? And again, my tip for tackling this is going ahead and drawing the lone pairs. Like for this oxygen, draw the 2 lone pairs. For this one, draw the 2 lone pairs. For this nitrogen, draw the 1 lone pair. It does matter. All right. The degree of unsaturation, memorize that form. You have to memorize that form, at least for the first test. So I'll compromise here, or we'll compromise here. The degree of unsaturation, you will know the formula by the end of OChem, but for this first test, just memorize it, and you're welcome to throw it outside of your brain just for a little bit. Just short-term memory, just memorize that stuff before the test. You're fine. These are a lot more conceptual stuff, like your problem set. What is the shape of SO2? Well, that's on your problem set. I'm not gonna give you guys the answer. Unless you come to office hours. Here's a very good one. Circle the strongest base. Now this goes into the inductive effect, right? So the strongest base is the weakest acid, right? And the weakest acid is the least electronegative. That's the logic here. Okay. Try to annotate. All right, cool. So again, strongest base, you're looking at this like, how do I figure out the strongest base? What will accept the proton more? That's a good way to look at it. But for me, I kind of work my way around because acidity rules are really easy to understand, better than base rules. Excuse me. So the strongest base would be the weakest acid. And the weakest acid would be the most activated system. Because, for example, I will say this right here, chlorine. Oh, wait, no, it'd be the other way around. No, yeah, this is positive end. Chlorine is pulling electronegativity towards itself, right? So if electron density is being pulled towards chlorine, that hydrogen that would be there is being deactivated more because all that electron density cloud in this bond is going towards that way. So the hydrogen will leave. Is a lot more protic, right? That means it's a stronger acid, weaker conjugate base. So it's not a strong base. So putting halogens on that alkane makes a stronger acid. which is now opposite of the strongest base. Now we're looking at this. All right, we have an oxygen and then we have a nitrogen or amine group. All right, which one is the most protic? That would be oxygen. You're also welcome to look at your pKa chart. That will help you in this situation. Oxygen is a lot more electronegative than nitrogen if you look at periodic tables. So that imaginary hydrogen that was there before left a lot easier than this. So this is a stronger acid than this. If this right here has a stronger acid, it has the weaker conjugate base. And if this is the weaker acid, it has the stronger conjugate base. So the correct answer is this one. Yeah. I'm going to stop this recording here. All right. If you have any questions, don't forget, just email me. Hopefully I didn't ramble on too much. I'll make sure to drop a message, make sure you guys watch on like 2x speed, because I am a little slow and technology inept at sometimes. So sorry about that.